Bom, quem faria a entrega da próxima homenagem seria o coordenador do Comitê Científico da EMECR, o professor José Carlos D'Abreu, mas como o Noudinho e o Leal já citaram, ele teve um imprevisto e não pôde estar presente. Porém, ele enviou um vídeo para falar sobre o próximo homenageado, o criador do processo Tecnored, o Marcos Contrucci. Vamos ver o vídeo.
Good morning, everyone. First, I'm very glad and honored to present this tribute to Professor Contrucci, a longtime friend. I knew him in the early 60s, when I gave my first step in the iron steelmaking field. In the next decades, our technical and scientific cooperation always were very intense and rich. First, to develop the several technological stages of the Technonet process, from the laboratory studies to the IDP, and recently to conceive the new technological proposal of the GaviaTech startup, subject of his plenary conference shortly. Contrucci is a Carioca citizen, a nickname given to those born in Rio de Janeiro, city where he raised and shared his passion for astronomy with the famous Brazilian architect Oscar Niemeyer. In 1964, he graduated in metallurgical engineering at PUC-Rio, and as partner of Tecnometal Engineering Company, he made many basic design studies for steel plants in Brazil and other countries. His passion for self-reduction smelting mold dates back to the early 70s, when he first proposed the Technonet process to be developed by a joint venture of different iron and steel industry companies, having our Iron and Steelmaking Research Group at PUC-Rio as his closest technological advisor. More recently, we share the GaviaTech technology patents, whose a third of its rights have been donated to PUC-Rio endowment funds in recognition to its extended support of self-reduction along the last decades, also always backed by ABM. Contrucci is married to Mary and has 4 daughters, a stepson, and 2 grandchildren, and lives in Rio at 2,000 feet altitude inside the Tijuca forests. This is Professor Contrucci, a true visionary leader and a very special guy. Congratulations, Marcos, for his fair tribute.
Bom, a gente espera que o professor D'Abreu se recupere rápido, né? Convido ao palco, então, o fundador da GaviaTech e um dos homenageados do dia, o criador do Tecnored, Marcos Contrucci.
Quebrar o protocolo aqui, eu tenho que dar um abraço nesse cara.
Well, first of all, I must say, I'm not talking for myself. Group of people, D'Abreu, Pedro Carpinete, Henrique, José Adilson, Ciro Tacano e Mourão, um grupo de professores que sempre estivemos ligados a esse fenômeno, a esse processo da autorredução, tão pouco conhecido, é uma espécie de jabuticaba, só tem no Brasil. Mas não pode esquecer que um grande incentivador que eu tive desde o início foi o PNAC. No ano 2000, nós podíamos ter tido o PNAC como um dos esteios do nosso grupo, mas a Mittal não tinha nada no Brasil naquele tempo, então foi impossível. Mas essas parcerias, elas são naturais. E o PNAC me incentivou ao longo de todo o tempo, ao longo do desenvolvimento do Tecnoed, e tenho certeza que daqui para frente nós vamos ter também. Tal como o Júnior, eu vou ter que prosseguir em inglês, porque é assim que está o nosso paper. É uma missão difícil. Convencer que um bandido pode virar herói. Porque, vamos ser francos, nós estamos hoje todos vendo o alto forno como o grande culpado das emissões de 2 toneladas de CO2, mas nem sempre foi assim. Ele foi realmente o nosso grande aliado. Eu costumo dizer o Old Faithful, mais de 200 anos, ajudando na Revolução Industrial e viabilizando o steel. There we go. What is the blast furnace right now? It's a gas-solid reactor. What's his mission? He generates gas in the bottom and expects the gas to penetrate a stone. It's not an easy task. And because it's not an easy task, it takes a very high stack. Why? Because it takes time. So it's very easy to say. Why a blast furnace is high? Because he is slow. And why he is slow? Because it takes time to a gas to penetrate the stone. And why does it need coke? Because it's high. You see, it's a circular problem we have to solve. Okay, but this is the guy we have. We teach at blast furnace for almost 30 years, myself at PUC Rio, plus Abreu, and help with Ciro and Mourão here and there. And we always made points on the excellence of the furnace. But he was like that. And if you see, the lump ore was his main charge in the mid-50s of last century. But progressively, lump ore ended. So stones got scarce. What was our reaction? We made artificial stones, which initially the sinter and finally also pellets. So by the end of the 20th century, we had the Old Faithful, still with the same gas-solid mode, but now using stones made by the owners, by ourselves. So this is what became a blast furnace plant. A blast furnace, a sinter plant, a coke plant, and in time we had PCI and oxygen as a reduction of coke as an economical imposition. But let's be fair with people that did it. I love this graph by Bodo. Bodo must be somewhere in the audience. And it shows what a beautiful job we made. See that from the 60s, here's where I started giving classes. We talk at 600 kilos of coke as a normal thing. And then we started overall blast furnace in Europe, started importing overseas rich ores, especially the trend led by Japan and Europe. And this is when Vale started producing, and also Rio Tinto, they started sending overseas high-grade ores. And there came the oxygen enrichment, top pressure, burden distribution. We started using computer models to gas flow control. We started improving the FEA burden, improving our coke, and more recently, we've been using small coke in the burden. And don't forget that by the 80s, we started also using the 2 years to inject extra fuels, much cheaper than coke. So this shows two things. First, blast furnaces are very flexible. Don't forget that in the 18th century, they were charcoal-based. In Napoleon times, it was converted to anthracite, then to coke, and it's almost 2 centuries now based on coke. And this is the paradigm that self-reduction intends to solve. Why? You possibly remember the odyssey of the Apollo 13 mission to the moon. 50 years now. Early June it made 50 years. And what happened? There was an explosion of an oxygen tank. They had to return. Bringing back the spacecraft was not that problem. You know what the big problem was? Was CO2. The building up of CO2 inside the lunar module, which was there. They had to cram three guys in the lunar module. And this gives a very nice analogy to what we are having now. Our spacecraft, the Earth, is not menaced. We are menaced. So the Apollo 13 group, they knew they could bring the spacecraft back to Earth in safety, if you wish. But how about the astronauts? This is more or less our case. This is where we are. And this is what we think is the solution. Pinaki made a challenge at the end of his presentation, saying that we need crazy stuff. He used to call me a visionary. Visionary was a slant up to Elon Musk. Now everybody loves visionaries. Okay. But this is the visionary vision. We believe we can, again, use the flexibility of the old faithful blast furnace and stop using coke and sinter and pellets, and in place, change this burden into self-reducing agglomerates and coal and carbon briquettes. What are the gains? The coke blast furnace use hot coking and sintering. The self-rat blast furnace would use coal-bomb briquetting. Low energy efficiency, you know why? You know how we make coke. We cook coal for 18 hours. And when it's ready, I agree, plastically it's beautiful. You push out the coke, take to a tower, and quench in water. Most of the plants, more than 90% of the plants, quench coke with water. It makes a beautiful nuke of steam. When I gave classes at CSN, my students love it to see this part. Okay, in those days, the barrel was at $2, $3 per barrel, so that was not a big deal of a problem. The same for sintering. We put sinter for 40 minutes or so at 1200 degrees C and happily bring it down to zero, just to burden back to the blast furnace. And when the blast furnace makes iron at an extraordinary improved process, we think he is the bandit, he is the culprit. No, sir. Culprit is using coke and using sinter. And this is what the self-read blast furnace intends to change. And what is our paradigm? Wow, our paradigm is, of course, Technored. Technored is doing this. You have a visit to Technored. 20 years back, I could have been acting in Technored. He knows that. And he tried. Here and there we meet, and he says, you see, if it was with us, you would have this operating. Okay, he's right. But it was impossible. But what happens when you change from coke and sinter into coal-blown agglomerates is that you gain a huge amount of credits. You increase very much. Just to give an idea, a normal iron-making section in typical integrated plants have a credit of around 4 gigajoules per ton. In just doing this, I'm talking coal versus coal, you get 11. Why? Because you're not using your gas to make coke. You're not using your gas in the hood to start making the sinter. And this makes a huge difference in cost. And what is self-reduction after all? Is the smelting of iron and other metals by built-in carbon inside agglomerates. It's a kind of stupid question. If we no longer have natural stones, and we have to produce our stones, why don't we put the carbon inside the stones? Is not that the end of the game? This is what self-reduction is all about. And what happened then? It happened that you get rid of coke, sinter, pellets, and you have a much faster dynamics. I was telling yesterday at the people that was at the Bloomberg Green meeting, I said my first glimpse of the really astonishing capability of self-reduction was when I was giving orientating a thesis of a student, and we made a pellet, a self-reducing pellet, and I told him, put on the muffle, and tomorrow we come and see how much of it is metallized. And he went there, and 5 minutes, then he came, Professor, it's all metal. I said, what? 5 minutes, 10 minutes to 100% metallization when it takes 8 hours in a blast furnace? That was a shock. And that was certainly a start of Technored there. Okay, and what happens? You get rid of the high temperatures of coke, sinter, and pellets. You have fast reaction rates. You have higher credits, lower OPEX. You use cheaper coal. You know how much was the quotation of coking coal last week in Dalian? $700 per ton. The normal is $250, about twice as much as thermal coal. And this is not all. Okay, the fact we have it, minutely divided, built-in reducing agent, no gas going through pores. We don't have to transport gas into pores. Only energy will travel, but energy travels through the walls. They don't need the pores. High reducing gas concentration. Remember, there's no nitrogen inside the agglomerates. And we have a compact smelting zone and an easy way out of CO2 produced from the inside the agglomerates. And a thing few people realize, we do not reduce individual agglomerates. What happens at by 700 degrees, the charge sinters. Sintering of the charge. The nightmare of blast furnace operators. I had the same problem. Pinaki have shown a very nice remembrance of showing that by the 70s, we are all saying that blast furnace were doomed for demise, and he decided to keep in serving the blast furnace with the competence he has. And this more or less happened in our case. So this is why. Well, okay, we have thermodynamics, but this is more Moron and Cyril that will give you. So we tested this, what this means if we change coal versus coal, coking coal versus thermal coal, and thermal coal gives a pricing for biocarbon, which is the essential point that will bring down our carbon footprint to zero, and perhaps to less than zero. In Brazil, this will represent 30% reduction. US East Coast, 73. 64 in Ukraine, not now. North of Kazakhstan, East India, and China. And you see the India and China is where the cost reduction is more intense. And why? Simply because power, electric energy, has a much higher value in India and China. We run this comparison more naturally. We didn't make it in the last few weeks because of the peaks of coking coal that we distort everything. So this is more or less an average of the last 2 years or so. And wait a minute, if we're talking converting blast furnace, we're talking converting the plant. So we worked with Usiminas. Cozipa plant has all its metallurgical part stopped right now. So we had the cooperation of Usiminas. And we know quite a lot because as an engineering company, we did a lot of work in Cozipa. So we realized that we put in new briquetting units using the blast furnace and making the transformations in the briquetting and in the coking plants. I used to kid saying, no, we will not shut down the coking plants. We'll use the coking plants, only they will no longer make coke. Why? Because the preparation of coal mix for the ovens, we can use. It's more or less the same for making coal briquettes, or biocarbon briquettes. And the same for the sinter plant. I used to say, no, sinter plant will be in use, only will no longer make sinter. They will make a mix for the self-reducing pellets. Well, so what, at the end of the day, look at what we are saying. We are saying that 130, no, it's okay. It's 130 to $180 tons per year. You will remember that J.P. Morgan made a very, very clever warning to us. They calculated that to replace blast furnace, as Pinaki has shown, it's about 70% of our industry there. You need $2.4 trillion. $2.4 trillion to replace blast furnace. We need this money for other things. to relaunch the economy after COVID, to address the difference, the inequalities that plague our societies. We need this money. Let's find a way that is profitable to change this. And we have made, with the Department of Energy, this was last year, a number of studies, because they have a bioeconomy concept. The point is, we have more carbon atoms available as wastes in the garbage, sewage sludge, and wastes of all kinds. We have this available more than we have every year. And they come from atmosphere. They do not come from the underground. And you can use, you see, forest residues, wood. This here was organized by Department of Energy. Dr. David Babson, that by the way we invited for this meeting, he could not come. But this is the challenge. And also for the garbage. See what is the problem? We have now more than 50% of garbage. This was made for the US. It's less in Europe. And it's going to landfills. And landfills ferment. And they ferment and give methane. And methane is just as a bad greenhouse gas as CO2. This is it. Again, we have the capacity of making a biochar worth $100, $150. This is a huge byproduct. You know, cement, bulk cement, is sold at $120, $130. And you know what is needed to reach cement to sell. While in garbage, waste-to-energy plant, it's just plugging a kiln operating at 400 degrees C, which is a bit more than a pizza furnace. Pyrolysis is a low-tech, low-temperature, low capex, and will give a high-value byproduct. This is why I say the hanging fruit are the waste-to-energy plants already in operation, because they have the logistics, they have everything set. This will be a very nice byproduct for them. And you can see that we're not talking fantastic technology advancements. It's a market advancement. Chris Saka, which is the inventor of the lower carbon capital, is working on this. And he says, guilt and sorrow will not solve the problem. Market will do it. And here we have to believe in the market, in the opportunities. The opportunities Pinaka have shown so much, so well minutes ago. Just to give you an example, you know where this biocarbon comes from? From garbage. This is the lone garbage treatment pyrolysis plant in the north of Minas Gerais. Why? Because a guy decided, made it. And look at this, beautiful biocarbon. And see how it ends up. This can be hauled. Remember, in Scandinavia, they have 350 million tons of residues, biomass residues. We're not talking planting biomass. We may well in the future, someplace, but not now. We have waste. Wow. So if you convert into biocarbon, including from those waste-to-energy plants already in operation, you can defossilize. We are creating this idea. It's not decarbonizing, which is the problem. It's defossilizing. Okay, I have 4 minutes. So what's the final proposal? And it's worse for everybody that makes charcoal blast furnace, because self-reduction don't need trees. We don't need trees, we need fines. So we say eucalyptus plantations in time can be moved to pulp and plant. And we go for fast cycle grass, bamboo, fast cycle biomass for the iron making. Okay. So now again, here we have a dream. As Martin Luther King once did, I have a dream. This is what we have. This is what PNAC have shown. Here is it. We get in the underground, we have it there, and we have all the efficiency. Huh? Don't forget, don't remember, we made tremendous efficiencies into the blast furnace in the last 30 or 40 years. But the carbon footprint is high. If we start, and this will not happen one day to the other. I used to say there is no silver bullet. We need all. You saw the enormous alternatives PNAC has shown. We need them all. The solution for the spacecraft will not come from one single place, from one silver bullet. It will come from a number of initiatives. And this is one of the initiatives. So we progressively will open the door to the steel industries to buy biocarbon. We put a board. We buy biocarbon. We pay well, $130 per ton. Market will come. Let's believe in markets. Okay, so we come to the point. I don't know if I'm talking 20, 30, 40 years ahead, but there was a time when we can get carbon footprints at net zero. And if we adapt all the streams to make ethanol and plastics, you possibly, PNAC have shown Lanzatec, that by the way is also working with ArcelorMittal. They have a place upstream into the pyrolysis of waste biomass, but also a place downstream. It's interesting because they can convert CO2 in plastics. They can convert all the streams in ethanol and plastics. Well, again, Carl Sagan, I'm an amateur astronomer, so all my examples comes from astronomy. Carl Sagan had a very nice statement. He said, for extraordinary claims, we need extraordinary proof. And this is the case. Nobody will change blast furnaces like this. So we are proposing that we make a group under the sponsor of ABM for math modeling first, and then to test our mathematics in a true size model. And this is what we intend to take as the final result of this fantastic meeting promoted by IBM, but attended by the greatest companies in Brazil and in the world. 7 seconds. Thank you.